everyone. In this video, we will start to learn chapter 8. So in chapter 8, we are focusing on called sample distribution. And so before this chapter, what we've learned so far, let's do a quick recap. So we're starting from learning about data and variables, and we're learning all those fundamental terms in the statistical world. And in that, the first 1 and 2 chapter we introduced for the statistic, we have two different kinds of statistics. One is called the discrete statistic. The other one is called inferential statistics. So therefore, for the first part of the learning for the semester, we're focusing on the discrete statistic, especially our chapter 3 and 4. We learn the data visualization and learn the numeric discrete statistics. So those are considered discrete statistic. And then after that, we start to move on to learn the probabilities and the probability distribution. Okay, so we haven't touched the inferential statistic yet. So that is what we're going to start to learn starting from chapter 8. We're going to start to look at, hey, when we're talking about the inferential statistic, we look at sample and the population. What is the in-depth about sample distribution? Okay, so for this chapter, we break it down into 2 parts. So in the first part, we are focused on learning the fundamental understanding about sample distribution, and then we need to learn how to calculate the confidence interval for the sample mean. Okay, at this point, you are like, wait, confidence interval for sample mean? I thought sample mean just one data, right? So we're gonna explaining what is called sample distribution. So that was a challenge for some of my previous students is they got confused because they're all thinking is, hey, the sample mean means one data. I calculate based on my sample, how the sample mean will have a distribution. So that is the first task for me is to try to help you to understand, hey, actually the sample mean is a random variable. And then when we move on to the second part, we're still going to look at the sample distribution, but we focus on the proportion. So that is relevant to our binomial distribution. So if you still remember what we learned from the binomial. So binomial is calculating the probability for the number of success, right? So divided by the sample size. So we look at the confidence interval for the sample proportion, okay, sample mean proportion. And then we're going to look at how large the sample size we need to have in order to have a good sampling distribution or generating more credible inferential statistics. So how large the sample size has to be. Okay, so that is what we're going to focus on in chapter 8. We are introducing the inferential statistic, but focusing on the fundamental understanding what is the sample distribution. So to understand the sample distribution, we need to revisiting about our sample statistic again. So the value of sample statistic and the calculated from the random sample will vary depend on which population items happen to be included in the sample. So here is trying to build a foundation to help you understand why our statistic will become a random variable. So let's imagine, and we have 1,000 observations. It's my population. Now I decide to creating a sample of 10. Okay, so therefore I go to this 1,000 population, randomly pick 10 observations. So that become my sample, right? And now I'm able to calculating the sample mean, sample standard deviation based on that 10 sample. And so that is what we learned before when we think about discrete statistic, use a sample to understanding. That is how we are calculating sample mean, sample standard deviation. But now when we are thinking about sample distribution, we need to think about this way. So we have this 1,000 population, and we went back many times. Each time we get my sample size of 10. So the first time I'll go 10, and the second time I went back out of 10. The third time I'll go back out 10. So each time I got a sample of 10, and each time I'm able to calculate sample mean, sample standard deviation. So when we're talking about the sample distribution here, we mean by, hey, instead of focusing on that one sample, we look at all the sample of 10 together, and then to calculate each sample mean. Now you can see the sample mean itself is no longer just one data point, right? It's going to be many data points, depends on how many times you go back to your population to collect the sample of 10. So therefore, in this chapter, what we are focusing on is that the sample statistics distribution. So that sample mean, how that sample means distribution should look like. So for that sample mean, what is the mean of the sample mean? What is the standard deviation of my sample mean? Because we are focusing on going back multiple times to creating my sample. And then based on each sample, we calculate the mean, standard deviation, and then we put all those sample mean in a new data set called the sample mean. So as you can see, they will be able to have its mean and the standard deviation. Okay, so that is the main difference from what we learn, what we're gonna learn and what we learned so far, right? We are thinking about this process as going back multiple times to creating sample, calculate sample mean. That each time we calculate sample mean, we're creating an observation, and for that observation is the value for my sample mean, and I'm able to calculate the mean of the sample mean and the standard deviation of the sample mean. Okay, so hopefully this will help you to understand, hey, what's the main difference between what we learned so far and what we are learning in chapter 8. Okay, so I'm gonna show you another example to help you better understand what do we mean by sample attribution. Okay, some sample may represent the population well, while other sample could differ greatly from the population, and particularly if the sample size is small. So this sampling variation can easily be illustrated selecting random sample from a large population. Okay, to help you to understand this, what I mean by sample distribution, let's look at this as example. Okay, give you another example. Consider sampling from a large population of the GMAT score for MBA applicants. So some students are going to ask, hey, what is the GMAT? So if you're thinking going to MBA program, and the several highly selected MBA program in the United States, they require this kind of standardized test called the GMAT. And so it's a little bit like your SAT score. So if you are international student, you take like something like a TOEFL. So it's a standardized. So this is a standardized graduate student test if you are going to the business school. So a lot of MBA program require the applicant to take this one. So therefore, when you think about the population of the GMAT score for MBA applicant, that will be very large, very, very large. Okay, so here on this slide, I give you information about this population. So the population parameter are mu. Remember, before when we talk about population parameter, we are using the Greek letter. So the mu here is the population mean equal to 520.78. And the population standard deviation equal to 86.80. And so you can see on the diagram below, it is the population distribution for the GMAT score. And it's a bell curve and all very look like a normal distribution, right? Look like normal curve, bell-shaped curve, and look like normal distribution. Okay, so this is about population. Again, we're using this example to help you understand what is the sample distribution. Therefore, we need to talk about, hey, I'm gonna creating a sample. So instead of using all the data, and I decide, hey, I just want to use 5 observations from my population. And then from there, I want to understand what is the mean of my sample and what is the standard deviation of my sample. So what I did here is, instead of just going back my population, draw the data once, I did it 8 times. So each time I sample 5 applicants to look at their GMAT score. To help you to visualize this process, and you're able to see on the right hand side this diagram. Okay, on this diagram. So each row here is representing one of my sample. So the first time I went back, I got 5 observations. 1, 2, 3, 4, 5. And so for instance, for the first one, the score is about 545 because it's above 545-ish. And so each circle means one of my observation. For my first sample, I also calculate a sample mean. And I use the triangle to denote the sample mean for my first sample among these 5 observations. So one thing you notice that I'm missing one of the circle because for my first sample, coincidentally, this triangle is also one of my observations value. So therefore, there's overlapping between my sample mean and my observation. And so my sample mean is around here. It's about 570, about 570. And then I went back again to my population. I randomly draw another 5 applicants to look at their GMAT. So those are the 5 applicants' GMAT score. And then I calculate their mean, which is symbolized by this triangle. As you can see, the 5 observations here and my triangle is here. So that means in my second sample, none of my observation coincident with equal to my sample mean. So therefore, the sample mean is this triangle. Okay, so I did the same thing 8 times because I have 8 samples. And on this diagram, this dotted, the dashed vertical line is showing where is my population mean. We already know the population mean given the previous slides is equal to 520.78. That's the score for the population mean. So what I want to show you on this diagram is to help you understand, hey, what do I mean by sample distribution? Let's just focus on the sample mean itself, right? So each time I'm able to sample 5 and I'm able to calculate the sample mean. When we're talking about the sample distribution, we are focusing on the statistics distribution. In this scenario, the statistic we're looking at here is my sample mean. So those triangles. Okay. As you can see that none of the triangles are directly on this vertical line, right? That means none of my sample are able to obtain my population mean. It's not surprising, right? That's called every time we sample, we will have some kind of variation, and we will have the sample mean kind of close to my population mean. Okay, population mean. So when we're talking about the sample distribution, we no longer focus on the observation itself. We focus on the statistics itself to see, hey, what distribution it will be formed. So you can imagine instead to do 8 samples, and I can do 1,000 samples. So I went back 1,000 times. Each time I get 5 observations, and each time I'm able to calculating the value for the sample mean. So when we look at the sample distribution, we are focused on that sample mean. So you can see the sample mean now become a new random variable. For my sample mean, it will have its mean and its standard deviation. So that is what we are focusing on in this chapter, is the statistics distribution. It's a statistics mean, statistics standard deviation. So later I'm going to introducing other terminology because it's kind of awkward. Keep saying the mean of the statistic, the standard deviation of the statistic. So we want to give a better name so that we are easily to call it versus keep use the same term again and again and get confused. Okay, so hopefully this example help you to understand what do we mean by sampling and sampling distribution and what we try to estimate. Okay, so in this chapter, we try to estimate what is the mean of my mean, what is the standard deviation of my mean. So in another term, when we're talking about sample distribution, is to look at the statistics distribution. Okay. After you understand what do I mean by sample distribution, and I want to talking about when we look at those variation, right? We calculate each sample, we see none of the sample mean are exactly equal to my population mean. And so what causing that? And when we can making that variation become smaller. Okay. So in the larger samples, the sample mean would tend to be even closer to mu. So in the previous geometric example, I'm using sample size equal to 5. What I want to explain here is if we are able to increasing my sample size, and then when you calculating that sample size, sample mean, you will notice that it will getting really close to my population mean. Okay, to make it extreme, so instead of just pick 5, you can pick the sample size equal to population size. So in that scenario, you can imagine your sample mean will equal to exactly your population mean, right? So therefore, it's not surprising as you increasing your sample size, you should see that sample mean will get closer and closer to your population mean. Okay. So to summarize what I just mentioned, a population distribution that describes the value of the sample statistic calculated from all possible sample of size n is called a sampling distribution. Again, the sampling distribution is focused on the statistics distribution. And as we already see, each sample will have variation from the actual population mean. So what might be causing that? Here we are introducing 4 factors. So the first factor is called the sample variation, because each time you go back randomly select your sample size, so you know that every time you calculate sample mean, it will be different. It also means it will be slightly or highly different from your population mean. So therefore, this sample variation is not controllable. So uncontrollable because it's a random sample. And the second reason might causing the variation is due to the population variation. So the population data itself are different, right? So every time you go back, since the data are different, you might get different data. So if your population have exactly same number, I don't think you will have any variation when you go back to sample, right? So because you just get exactly the same number. So because the population itself have varied numbers, and therefore you will have variation when you have your sample distribution statistics. So therefore the second factor is also uncontrollable. So what we can control as a statistician or data analyst are the following two factors. First is our sample size. So you can decide how large a sample size you want to pick. 5, as I said, kind of small. If you can enlarge a little bit, and when you do your calculation for your sample mean, you might getting closer and closer to your population mean. But of course, you don't want to get exactly same size as your population, because that's your waste the advantage of your sample, which is save your time to collect data, right? So the second factor that you can control is a desired confidence in estimate. This is also controllable. So I would just leave this one here because later we're going to look at the confidence interval, where we're going to introduce more what do I mean by desired confidence. Okay. So now after we understand sample distribution, let's introduce more terminology that will help you later down the road to understand the sample distribution better. So the estimator versus estimate and versus parameter. So this part of the diagram or concept is relevant with what we look at in the chapter 1 when we look at inferential statistic. And I developing that diagram where I connecting population with the sample, sensor versus sampling, statistic versus the parameter. So basically, it is a very similar concept here. But we just want to redefine the term. First, it's called estimator. So the estimator is a statistic calculate from the sample to estimate the value of the population parameters. So basically, this estimator is my statistic. So the estimator is my statistic. Remember before in chapter 1, I mentioned parameter is used to characterize the population and the statistic is used to characterize the sample. So instead of calling statistic here, we kind of try to make it more clear. We call statistic as estimator. So they are the same concept. Okay, so for instance, on this diagram, so the population parameter mu, which is population mean, and then we use the population mu to characterize my population data. And then when we move on to the sample, based on the sample data, we are able to calculate a statistic called X bar, the sample mean. So that is my estimator. Okay, so the estimator is used to representing my or characterizing the sample, and then the parameter is used to characterize my population. Okay, so next is called estimate. So an estimate is the value of the estimator in a particular sample. So after, based on the sample we collected, we are able to get in that number. So that number become the value called the estimate. So the estimate is the value of the estimator. So for instance, I go back to look at a geometric example. So first of all, for each sample, I'm calculating the sample mean, X bar. So that is my estimator. So when I look at a specific sample, sample 1, what is my estimator's value? So we got 570, this triangle, right? That 570 become the value for the estimate. So the estimate of my population mean based on the sample 1 is 570. So right, 570. Okay, so that is the relation, the meaning of the estimator and estimate. Okay, so and we are using since it's related to the inferential statistic, so therefore the estimator is the statistical inference for my population. What does that mean? So if we have a good estimator, once we know the estimator's value, the estimate, that should be able to tell us what is the population parameter value should equal to. Okay, let me repeat one more time. So our main goal is trying to understand the value of the parameter, right? But sometimes it's very cost ineffective to understand every value in the population. What we decide to creating sample. And after creating the sample, and we are able to, based on the sample, to getting the value for my estimator. So if the estimator itself is a good estimator, And so it means that statistics are good inference to my population. So once we're able to get in the value for estimator, we will be able to use that value to say, hey, that value will be able to use to representing my population's parameter value. Okay, this is the logic. So we are not directly getting the value for mu and sigma. We're detouring. We get value from the sample, and based on the sample, we try to guess, hey, based on the value, we try to say, hey, if this estimate can be used to representing my population parameters value. Okay, so that is the relationship between population and sample, how we are leveraging the estimator's value estimate to understand the population parameters value. Okay, now you might have a question. How do I know the estimator is good or not, and whether we can trust it to believe the value of my estimator can be used to representing the population? So therefore, that is what we're going to look at in the next is about the quality of the estimator. Okay, before we move on to the quality of estimator, I want to show you this table. This is the summary about the three estimator we are looking for, and we try to understanding their sampling distribution. So the first estimator we are looking at is my sample mean. And we already learned how to calculate sample mean in our chapter 4, the numerous statistics. So this is the formula we use to calculate sample mean. And so this estimator is an inferential statistic for my population mean. And then later on, we're going to look at, hey, given we know the sample mean, and how do we know the sample mean's probability distribution? And the second estimator we're looking at here is called the sample proportion. Basically, the sample proportion is the probability of success. It is equal to the x divided by n. So the x representing the number of success, and divided by the n, that is the sample size. Basically, the p here is the binomial distribution we already learned, the probability of the success. So we want the estimator is based on the sample proportion, and that is the estimator for my parameters. Population parameter is the population's proportion of success, which is pi. And then third estimator we look at here is the sample standard deviation. S, we already learned in chapter 4, that's how we calculating the sample standard deviation. And that is the estimator is used as a statistical inference for my population standard deviation, sigma. Okay, later on, we're going to look at how we're leveraging this estimate to help us to understanding the distribution of the sample mean. Okay. Now, let's look at the three properties that we need to use to judge if the estimator is a good estimator for my population parameter or not. So before we look at the three properties, we need to introduce a concept called a sampling error. So what is a sampling error? So the sampling error is the difference between the statistic and the corresponding population parameter. So if I use the formula to calculate this, we are using the sample mean of specific sample minus the population mean we already know. That will give us the sample error. So the sampling error exists because the different sample will yield different value for the sample mean, x bar, and then depending on which population item happen to be included in the sample. So I'm going to use the GMAT example again to show you how to calculate the sampling error. So for each sample, here we have 8 samples. That means we will be able to calculate 8 sampling errors. So for my first sample, after I got my 5 observations and I calculate sample mean, which is 570 here, right? 570. So what is the sampling error for my sample 1? So it's equal to the x bar, which is 570 minus 520. So that gives me 50, right? So therefore, the sampling error for my sample 1 is 50. Okay, now we move on to the second sample. So for the second sample, my sample mean triangle is here. It's about 560. So I just approximate it. Okay, it's about 560, right? So then the sampling error for my second sample will be equal to 560, this triangle's value, minus 520. So the sampling error for the second sample is 40. Okay, the sampling one is 50, error for the sample 1 is 50. Sampling error for sample 2 is 40. And you can do the calculation for the rest. So you totally will be able to get 8 sampling error here. Okay. So after you know what is sampling error, as you can see, it's really due to every time you go back to sample, you get different number in your sample, and that result you get in different value for the X bar, and the difference between the X bar and the mu give you a sample error. And now we can start talking about the first property called the bias. So the bias is the difference between the expected value of the estimator and the true parameter. Okay, so we are using the sample mean, this estimator X bar as example. Remember go back again. So the X bar is supposed to be the estimator for mu. So when we're talking about the biases, we are looking for the expected value of my X bar, and the expected value of that, how far away from that from the population parameter that we try to estimate, right? So the mu. Now I want to help you understand what's the expected value of X bar, what's the difference between bias and the sampling error. So the sampling error we just covered is for each sample, we are able to calculating a sampling. We are able to getting the we are able to getting a sampling error. But when we're looking at the biases here, instead of looking at the one sample, we look at all the samples, and then what is the average mean from the population mean. So how that works. So when we calculate sampling error, we are looking for each sample will have its sampling error. When we look at the biases, the first step we need to do is adding all 8 samples, sample mean together, divide by 8. So that will give me the average of my sample mean. So like I said, we don't see the mean of the sample mean, kind of a little bit like a riddle, so kind of confusing. Instead of the mean of the sample mean, we call it expected value of the sample mean. Okay, so the expected sample mean means you adding all your samples, sample mean together, divided by the number of the sample you have. So in this case, I'm adding all triangles number together, divide by 8. That will give me the value for expected value of X bar. And then using that value minus my actual population mean, that will give me the biases. Okay, so after you know what is biases, now introducing the first property of my estimator. So if your estimator is good, it's supposed to be unbiased. So that means your expected value as X bar minus mu equal to 0. So there is no bias. They're therefore called unbiased. So that means the expected value of your parameters, expected value of your statistic, your estimator is supposed to equal to your parameter. So that means your estimator did a good job to figure out what is the population parameter value supposed to be. Okay, so here we want to let you know, based on statistics theory, and since we are undergrad level, we are not go through, hey, how you prove it. So the X bar, the sample mean, it is an unbiased estimator to the population mean. So that is the one thing you need to remember. When we think about the X bar, that is the unbiased estimator for the population mean. Okay, so this is the first property called the unbiased estimator. The second property I'm introducing for the estimator, a good estimator, is called efficiency. Remember for the bias or unbiased, we're focusing on the expected value, basically the mean of the statistic, the mean of the estimator. So when we look at the efficiency, we're focusing on the variance of my estimator. Okay, the variance of estimator. So efficiency refers to the variance of the estimator of sample distribution. So if my estimator is the most efficient one, that means among all the estimator, that estimator have the smallest variance. So basically, the smallest variance means it's very close to the expected value. So here I want to use this target as example to help you understand what we mean by efficient or smallest variance. On the first target, as you can see, we have all my estimates value estimate so all my you are able to see all the estimators value in the center, And if you look at they all, first of all, the mean of all those dots is in the bullseyes. But the second is all the dots are inside the bullseyes. For the second target, although the mean of the shots are in the bullseyes, however, when you look at for some of the dots, actually is outside the bullseyes. So the first one has less variation, the second one has larger variation. So when we're looking for the estimator, that is has a minimum variance, and we are looking for the first one because the first one has way smaller variance because they are very close to the center. So that's what we want to say is if the estimator is unbiased and also had the smallest variance, and so that's the second property you need to check is make sure they have the smallest variance. And then the third, so you cannot assess efficiency from one sample, but it can be studied either mathematically or by simulation. So statistics have proved that for normal distribution, the X bar and the sample variance and sample mean are minimum variance estimator of mu and the sigma square respectively. So again, we are not going to dive into further about why sample variance is the most efficient estimator for the population variance. You just need to remember that's the case. Once you are able to obtain your master degree in statistics in those programs, you will learn further how to prove it. Okay. So the third property for the good estimator is called consistent. So a consistent estimator converges towards the parameter being estimated as the sample size increases. So that is the sampling distribution variation decrease around the true parameter value as illustrated. So the figure illustrates the importance of the larger sample because in a larger sample, your estimated mean is likely to be close to your mu. So basically the consistent estimator means regardless, it's not as you are increasing your sample size, you will find your sample this estimator's value getting closer and closer to the true population parameter's value. In that situation, the estimator is very consistent. Okay, so those are the three properties we want to check when we have estimator in order to know whether they are the best estimator to representing the population or not. Okay, after you know the three properties, and I want to show you the example to help you further understanding how to check on the three properties. Okay, let me go back to my three equation here. So we already spent time to talk about the sample mean, X bar. That is the estimator for my parameter mu. So the X mean had no question. It is unbiased. It is most efficient. And it is also consistent. As your sample mean get larger and larger, X bar will become mu's value. Now I want to challenge you to think about the sample standard deviation. Does sample standard deviation check all three boxes as well? Okay, here's the answer. Sample standard deviation only check two boxes out of three. It will check the efficiency box, as I already mentioned in the lecture. The sample standard deviation, it has the smallest variation among all the other estimators you can find to estimate the value for the sigma. And also sample standard deviation will be consistent. As the n sample size getting larger and larger, so the S value will approaching and equal to sigma's value. However, sample standard deviation is a biased estimate. Why is that? Let me explain it. So back to chapter 4, we already looked at the formula to calculate S versus sigma, right? So S and the sigma, even on Excel formula, there are two separate formulas because the calculations are different. So for the S, instead of divide by capital N, we divide by N minus 1. For the sigma, we just divide by population N. Because that differences will result your S will never equal to sigma, especially when the sample size is small. I know when the sample size getting larger, when this n getting larger and larger and larger, that difference will become smaller and smaller, but the difference is always going to be there, but the difference is going to become 0.000000001, maybe that kind of small, but the S will never exactly equal to sigma. Okay, so therefore, the sample standard deviation is a biased estimator for sigma. And you're going to ask, hey, Dr. J, why people don't create other method to estimate the estimator to estimate sigma? The answer is, although S cannot check all three boxes, but that is the estimator is the most efficient and most consistent. And so we are impossible to find any statistic estimator that is unbiased and also check the other two boxes. So therefore, keep in mind for the sample standard deviation, we are able to check the two properties of the best estimator. We will sacrifice the unbiased requirement. Okay, we will sacrifice unbiased requirement. So that's the end of this video. Hopefully it helped you to understand what we are learning in this chapter, sample distribution. So in our next video, we're going to focus on called the central limit theory, and then we're going to move on to the confidence interval for my sampling statistic.